Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. Having discussed the force transmissibility in a typical multi-degree of freedom system in the previous session, we are going to take a numerical example based on what we discussed last, and that will help you understand the concept better, and this will be followed by the discussion on lateral or bending vibrations of typical structures like beams or rotating shafts using the concept of influence coefficient. Okay, there is an example that we would like to now take based on the concepts that we learnt till now on the transmissibility of this multi-degree of freedom system. So, it's a long example to read. So, I would leave it to you to extract relevant information, but we are going to only discuss some of the important part of this problem solving, and the actual solution is something which you can work out yourself and then check whether the answers are matching or not. Basically, it is asking us to figure out what are the natural frequencies of a system which is like a motor mounted on a concrete block that you see here, and this motor is generating excitation. Obviously, maybe the CG is located somewhere here, and it is quite similar to the box vibration case that we discussed a few slides back. So, it is going to have x degree of freedom like this, the theta, and of course y. Okay. Things are quite similar, except that you are given the numerical values of the relevant parameters, and you are supposed to solve it. Solve it for natural frequencies, forced vibration amplitudes, and more important from our discussion right away is going to be the value of transmissibility or transmitted force to the ground, that is the part C. And then he asks us to re-evaluate the force transmitted if we manage to ensure that this CG is somehow relocated so that it is aligned or in line with the springs. Either you relocate the CG or you shift the spring position so that it is aligned with the CG location, which essentially means re-evaluate for the condition Ay equal to 0, right, and check for yourself whether that generates lower level of transmissibility as we have discussed in few slides back. So, I will only highlight some of the important aspect of the evaluation process. For example, the first part was to find natural frequencies, and I think we discussed these equations how they are being arrived at. So, p x theta 1 and 2 can be obtained from this expression, p y can be obtained from this, and p x can be obtained by including the stiffness ratio parameter by the expression which has been already discussed. Okay, now similarly the forced vibration amplitudes, again you can use the expressions that we saw last time, and that basically results by appropriate substitution of all of these parameters which you can find in the example given. It turns out to be amplitudes are minus 0.0608 millimeters, and the pitch amplitude is given by this. So, these are all just numeric values which are straightforward to obtain from the expressions. The most important part is to figure out how much is the force transmitted. Now, we discussed that in the form of a figure or a graph in which we saw how decoupling of these modes can bring down the transmissibility, but that was qualitative discussion. We never looked at the expression for the transmissibility, right. So, what we are going to look at is how to find that transmitted force. So, if we focus on one of the mounts, so obviously this concrete block is supported as at the four corners. So, you can refer to the figure that we discussed in the previous slides. And so, if G is located here, this is the plan view of course, and so this position of the spring would be this distance which is AZ and this distance which is AX. So, for a positive AX distance, and if you look at the elevation part, the position AY is going to be negative because Y is considered positive upwards that way. So, this particular spring position, let us focus on this particular spring position, and that position is given by this coordinate plus AX minus AY. That those numbers or the values are already listed in the example. For this spring mount location, let us find what is the force transmitted through that spring connection. So, the force transmitted is given by this expression. Okay. You can find this because we have solved for the forces which are acting on a free body. So, you can very well recall that it was kx ay theta. Now, you will have to use appropriate phase relation between theta and y and x. Okay. If you remember or recall the expressions and the value that we have got, x and theta, they are in phase. You see that they are in phase, both of them have negative values, and if you look at this expression, it basically says that the force transmitted along x direction because of the theta motion and because of x motion. Now, x is like horizontal shift of the whole body, okay, and theta is going to be the pitch motion, both of them in phase and both of them will reach their peak values at the same time, right. So, cos omega t is being used here to get the instantaneous value of the force transmitted. Okay. It should also be kept in mind that the force is rotating like this. So, its cos component and sin components would look somewhat like what I have shown. Similarly, in the y direction, the y component and theta component, they will have to be used with cos and sin component. So, when the unbalance reaches 90 degrees up, the force along y direction and the movement along y direction will be peaking. So, these relations of the sine and cosines involving sine and cosine terms should be appropriately used, and the signs here are important and they will come from the phase relationship between the amplitudes of x and theta. Okay. Y of course is decoupled, it is going to be independent motion. Now, having obtained this Ftx and Fty, that is the force transmitted through the spring to the ground, they will be having its they will be dependent on the speed of rotation of the motor. So, it is going to be time dependent force in x and y direction, all right. Now, to find the maximum value transmitted, we will have to get the expression for the transmitted force. So, the transmitted force through this will have its x component and it will have its y component, right. So, the net force transmitted will be the vectorial sum. Okay. So, we can use the total force transmitted using this expression, and this force transmitted again will be time dependent force. Okay. Now, if I want to find out the maximum force transmitted, because our transmissibility Tr, okay, due to force will be what? Force transmitted divided by the applied force F naught, is not it. So, if you want to do that, you will have to actually get this expression by substituting appropriate numeric values. So, you will have to get an FTR expression, which will be square root of these two expressions being used and appropriate values of kx, x and omega being substituted there, right. So, this is going to be again a long expression, but if I want to find out the maximum force transmitted, what am I supposed to do? I will have to find out how much is the maximum force by setting this derivative to 0. Okay. When you get the instantaneous transmitted force and it may vary, then I can find out the maximum force by taking a derivative with respect to omega t, because this is the independent variable with which the transmitted force will vary with time. And then I can get, by solving this equation, I will get the value of omega t, okay, for which this expression is valid, and that is what we want. What we want is what is the radial position at which the maximum force is transmitted. Is that clear? Okay. With this, we can obtain the FTR max, and then if you divide it by the implied force, we can find out the transmissibility, and those calculations I am skipping just to give you an idea as to how this is to be solved. So, once you substitute for omega t, which you can get by equating the derivative to 0 into this expression, use appropriate values of omega t for which this expression is valid, you get the maximum transmitted force, and that turns out to be approximately 115 newtons. And then if you use again the expression for transmissibility, or just divide this maximum force transmitted to the force going through that spring, but keep it in mind that this cannot be divided by just F naught, and 1/4 of that force is getting through the spring that we are talking about. So, it will be 1/4 of the force generated at the motor location. So, that will give you a transmissibility ratio of 1.73. What do you make out of this number? Right? It is more than 1, all right, and this is the case where Ay is not equal to 0, which actually means that if this is the CG position, this distance is your Ay, which is non-zero. What is our philosophy? We should try to get this Ay as 0, as low as possible, or theoretically possibly maybe 0, right. If I rework these these calculations for Ay equal to 0, physically how you realize it is a different thing, but if we suppose set this Ay equal to 0 and follow the same procedure, you get the transmitted maximum force at that spring location here to be 28.3. You can see how drastic reduction you are getting there, almost 1/4 of the force transmitted is reduced. It is reduced to 1/4 of the original value, and the transmissibility ratio drops to 0.43. Okay. So, that of course, as we discussed last time, that instead of like this kind of a configuration for a heavy machinery, either you support it here so that it aligns with the CG, or you shift the CG by attaching heavy mass here, so that instead of holding it or supporting it there, which becomes quite practically infeasible, then you shift the CG by attaching heavy mass, and then you bring Ay equal to 0 in this case. Okay. So, mathematically this is the ideal situation. Practically you can bring it as close to 0 as possible by appropriate supporting it. If you have a multi-cylinder engine on the chassis, this will be a worst way of supporting it. You can have some elements here, and the mount can be supporting it here on the sides, right, somewhere like that on the chassis, and then it will have Ay equal to as low as possible, and the coupling can be avoided to improve improve in the sense improve for the better the transmissibility ratio. That is the numeric part of it. I am not discussing all the steps here, but you can work that out based on the data given in the slide. Okay. Now, let us train our attention on another kind of a multi-degree of freedom system, now practically very important, and that is why it has to be discussed in this particular topic. A rotor which has multiple discs on it, right. Now, typical steam turbine rotor will have many stages, even the low pressure turbine or a high pressure turbine, all of them will have multiple stages. We have seen in one of the pictures that I showed you, but for the sake of discussion, if the number of stages can be limited, and then particularly considering the larger of them, maybe if you consider the rotor a flexible rotor with these two stages, the discs having blades on it and supported on the bearings at the ends. So, this is the configuration that we are talking about. We will have to now look at this problem slightly in a different way. So, this can be now a 2 degree of freedom system, because both these two discs can be assumed as point masses, okay, and they would have independent degree of freedom. So, I can consider this to be y1 and this to be y2, and y1 can happen independent of y2. So, we have this system as a 2 degree of freedom system. The shaft is assumed massless for the time being. We will discuss later on in this course how to get around with that limitation, but the moment you start looking at including mass which is distributed throughout the length, then lumping it also does not work out to be an accurate approach. So, we will find out through numerical methods how to take into account the shaft mass. However, let us look at how we attempt this problem. The shaft is massless, the discs have their own weights, and what we are going to do is, if you assume the system to be linear and the influence of the first disc is to start with accounted for by application of a force at that particular location. At that location, if I apply a force, then how would the shaft deflect? You have learned that in your strength of material, right, that course, that it will deflect something like that, okay, and the expression for the deflection is very well known. So, the deflection here is suppose defined as delta 1 1, which actually means that at location 1 the deflection is delta due to force applied at the same location, but this force also generates the displacement or a deflection at this location as well, right. So, this is your location 1 and this is your location 2. So, an application of force F1 at location 1 generates the displacements deflections at points 1 or position 1 as well as 2. So, at position 2 the deflection in the shaft at position 2 is going to be labeled as delta 1 2, which means the deflection at 2 due to force acting at location 1. Okay. Now, same thing can be happening for the force at disc location 2, and then you have these two deflections, right. When both of them are acting together, there will be a linear superposition of the deflections, and then the deformation of the shaft at location 1 and 2 would be given by y1 and y2. This is our static case where forces F1 and F2 are static forces acting on the shaft. Now, how do I find delta 1 1 or delta 2 2 and so on? Okay. Now, those are to be obtained through of course, strength of material will allow you to do that, but we define through that term called as influence coefficient. Probably you might have heard about them. What is that? It defines the deflection due to the force applied. So, if I am applying applying the force at this position on the shaft given as F1, and it causes deflection delta 1 1 here. Then the influence coefficient alpha is defined as the deflection due to force applied at point 1 when there are no other forces acting on the shaft. Okay, this is important, only one force at a time. So, one force acting at point 1 will generate the corresponding deflection. I am writing this as delta 1 1, and then for the sake of proper notation I would call this as delta 1 2, sorry, delta 1 1. So, I am sorry, this is alpha 1 1. Okay, alpha 1 1 represents the deflection at position 1 due to unit force applied at location 1. And on similar lines, obviously I can define alpha 2 2 influence coefficient as delta 2 2. Please mind you that this is not a square, okay, it is simply referring to the location per unit force applied at location 2, and most important part is that all other forces are 0 except that force. Okay. And as we see here that irrespective of the fact that there is no force acting at that point, there is a non-zero deflection there at point 2. So, we define the influence coefficient to 1 to represent delta 2 due to force 1, and that is how the influence coefficient alpha 2 1 gets defined. And obviously similarly alpha 1 2 gets defined as delta 1 due to the force F 2. Okay. So, due to force F 2 the deflection at the location 1 is through the influence coefficient alpha 1 2. Okay. With this defined, it is quite possible now to write the total deformation or deflection at point 1, and that obviously would be summation of this deflection and this deflection, assuming principle of superposition is valid, for which we are already declared that the system is linear, and obviously which also means that our deflections are going to be small in the amplitude. So, with that small amplitude assumption, y1 can be written like that and y2 will be written like this, right. Now, this is for static forces F1 and F2. So, we need to now map this or use this for our vibratory motion. Okay. So, the system is going to vibrate, and we take the example here that the system is vibrating in one of the principal modes, which you already now are aware of what does that actually mean, that the entire system vibrates with a harmonic motion with a particular frequency, and that frequency is one of the natural frequencies. So, we assume that these discs are moving in one of the principal modes or normal modes, and the natural frequency is defined as p for that. So, obviously y1 would be defined as y1 cos pt, and obviously y2 will also vibrate with the same frequency, we know that. The only difference is that based on the configuration, the amplitude of the second mass or the second disc could be different, y1 and y2. Now, what we do is, instead of these static forces, we can replace these with the fictitious force, the inertia force. Okay. So, F1 would be written or would be used replaced with m1 y1 double dot, m2 y2 double dot. Okay. The only thing is their directions will be opposite to y. Okay. So, they will be negative, but then by using this assumed motion, a harmonic motion, in these expressions they will turn out to be both positive. So, y1 will be alpha 1 1 m1 capital Y1 p square and so on. So, these expressions of y1 and y2 would now turn out to be as given here. okay, if you substitute those expressions. So, the y1 amplitude and y2 amplitude is going to be function of the influence coefficients, the properties of the system m1 and p square, and that is how these two expressions are obtained. Now, you can work that out. So, if you get solve this for y2 by y1, that means collect all the terms of y2 and y1 as a ratio on one side, you will get one expression. Similarly, this equation can also generate another expression for y1 upon y2 upon y1, simply similar to what we have done for the two masses coupled through the springs long back. So, these are the expressions, and obviously, when you get from one equation y2 by y1, from the other one another expression, you can equate them. That is how this expression shows. Needless to say, once we get these ratios, what are these ratios? What do you call these ratios? Yeah, they are mode shapes, right, because you are considering principal motion and you are expecting the disk 1 to have amplitude y1 and disk 2 to have amplitude y2. Okay. They may be in phase, that means both of the disks will move together down, okay, in one of the principal modes. In another principal mode, one disk will go down, one will go up, but the principal motion ensures that both of them will reach their maximum positions at the same instant of time, and their oscillations will have same period. Okay. Right. So, these are essentially the mode shapes for this system, and by equating the two right hand sides, this is what you can get. And then of course, when you cross multiply, what do you get? You get the frequency equation. If you cross multiply, you will get an quadratic in p square, that is what you see here. Simple mathematical manipulation will give you this characteristic equation. When you solve this characteristic equation, you get the natural frequencies, and obviously something similar to what we have discussed in the early part of the 2 degree of freedom system. And what do you use these natural frequencies for? You can get the actual exact mode shape by substituting by substituting either P1 or P2 in this expression, you get the first or the second mode shape, right. So, you can find out by using appropriate mass values and the flexural rigidity of the shaft, you can find out the natural frequencies P1 and P2. When you use one of the two natural frequencies in this expression, you get what is the relative amplitudes of the two disks when they vibrate in that particular mode of vibration, principal mode of vibration. So, you will get two mode shapes, and those mode shapes are y2 over y1 at P1, and the other mode shape will be y2 over y1 at P2. Okay. And with that you get an appropriate mode shape, and although you can find this out by appropriate numeric values, it so turns out that the first mode will show the mode shape to be this, which is expected, right. So, both the disks are going to move in the same direction, whereas in the second mode this disk can have this peak value and this disk will have this peak value, and so on. So, the second mode will be this kind of a second mode, where when this disk is moving upwards, this disk is going to move downwards, and so on, right. So, then your y2 by y1 will be negative basically. It is quite similar to x2 upon x1 that we discussed for a 2 mass case with specific stiffness values. This turned out to be +1, and then in the next mode, second mode, this turned out to be -1. You remember that? So, that masses were moving in the opposite phase. Okay. So, this is how these problems are to be solved for its natural frequencies and mode shapes. Let us consider one example just to highlight what we discussed as a background for attempting these kind of vibration problem. These are basically for lateral vibration of rotor bearing systems. So, this example says that that the system is like a turbo pump where the turbine drives the pump and the pump has an inertia. The pump impeller is located in the center of this shaft span, whereas the turbine is overhanging. So, this is very typical configuration of such turbo pumps, and all the data is given. So, the lengths are given, the shaft dimensions in terms of its diameter and length properties are all given, the material properties are given, and you can find from the strength of material that these influence coefficients turns out to be L cube by 6 EI as alpha 1 1. This you can find out from a beam theory where all the expressions are quite well documented, that if you have these kind of supports and then if you apply a force here in the center of the span, what is going to be the corresponding deflection, and then if you divide this deflection by the force expression, you basically get alpha 1 1, and that would be for this position. Accordingly, if this is the deflection, what is the deflection at this location, that also in the form of expressions are all known, right. So, once you dig out into those books, reference books, you can figure out what these expressions are, and these are the expressions for the configuration that is given here. Well, once you get these, your job is quite straightforward from here. We all know what is the what are the expressions for the mode shape and natural frequencies as discussed in the previous slide, but we are now going to look into the problem of finding out the forced vibration response. The way we did it for a 2 mass system, we tried to figure out what is the response to harmonic force excitation, right. So, what we are assuming, instead of complicating things, what we say is one of these discs are perfectly balanced. Okay. Maybe you can consider the pump to be fully balanced and turbine has some residual unbalance. That unbalance is going to create a lateral force which is going to be m e omega square cos omega t. So, that is basically your f cos omega t as the excitation force on this disc, right. You can as well consider the unbalanced excitation or any harmonic excitation at the other mass, but that is going to be quite similar to what we have seen in the multi-mass or a 2 degree of freedom 2 mass system, where the response due to one excitation you can add up algebraically to the excitation from the other mass by appropriately accounting for the phase between the two, if there is a phase, and obviously there will be phase difference of the excitation function here. Both excitation cannot be always in same phase. Those things aside, if we simplify the problem here to understand how the response to any unbalance or any harmonic excitation to such lateral vibration system is obtained, what we now say is that y1 is not going to be only given by this, okay, but we include the contribution from the unbalanced force. So, now this unbalanced force appears just like these inertia forces, right, and if it is supposed to be at location number 1, if we assume this to be the location 1, I think you can figure that out as to whether the alpha 1 1 and alpha 2 2 are corresponding to this or this. Okay. That having said, wherever this force is applied on whichever disk that we are considering, the corresponding influence coefficient comes into picture. If it is applied here, then that influence coefficient will be used in the expression, or the other influence coefficient like alpha 2 2. So, y 1 would be written like this, okay. Y 2 will be written like this, but do understand and note here that the same force will generate the response or a deflection at the location number 2, but the only thing is that that deflection will be governed by the influence coefficient alpha 2 1. Okay. So, if you have if you consider this to be the location and you are trying to find out the deformation here, it is going to be this, that you apply force here and get a deflection at this point delta, then alpha 1 2 would be delta over this f. Okay. So, even if the deformation is going to happen here, the deformation is also going to happen here, and if this force is the external force f of t, then you have to use the additional deformation to the total deformation at location 2 by including that term to the existing terms due to inertia forces. Now, what we do, we will have to assume a solution the way we always do. You know, this is a forced vibration problem. What will be the solution assumed? Will it be y 1 t capital Y 1 cos p t the way we did it in the previous case? It can't, because this is not a harmonic free vibration, it is a forced vibration, and the vibration is going to happen at the frequency of excitation, external excitation. So, this would have to be modified to y 1 cos omega t. Okay. So, this expression is now going to be of course rearranged to this, and then you use the assumed solution with the frequency of harmonic excitation. So, if you rearrange these terms, this is what you get as the governing equation of motion for a dynamic lateral vibratory motion of the shaft. So, I am just rearranging these terms on the left hand side the way we do it. The external forces which depend only on time goes to the terms go to the right hand side of both of these two equations, and then of course, you assume these two harmonic response solutions and then substitute the solution with their derivatives into this equation to get expressions in capital Y 1 and capital Y 2. And obviously, these are all what? These are the responses to harmonic excitation. It will be dependent on the magnitude of the external force obviously, and both of these are dependent on the magnitude of the external force F, and if unbalance is considered, then F is going to be u into omega square, where u is the unbalance which has the typical working units as kg millimeter. Okay. You convert that into kg meter and then use appropriate rotational speed omega to get the F value in newtons, and expectedly the amplitude with which the discs 1 and 2 will vibrate, that is dependent on the strength of the amount of unbalance in the discs. Okay. Now, if you find y 1 and y 2 based on the unbalance here, you can separately find out what is the unbalance F here and find out the response, add these two responses together, or use the equations with the appropriate modification to these equations with the alpha 1 2 and alpha 2 1 coming into picture. In that particular case, alpha 2 2 and alpha 2 1 1 2 will also appear if you want to include both of them simultaneously. But these are this is the way to find out the total harmonic response in the lateral vibration by utilizing the concept of influence coefficients. Quite powerful. In fact, if you look at these equations in y 1 and y 2, they are going to have in the matrix form the influence coefficient arranged like this, and that way you can use it for many discs on the shaft, okay, as many of the degrees of freedom that you would like to include. So, then you will have to figure out which stages are having larger mass, some of the discs which are smaller in terms of its mass or weight can be ignored for the sake of getting the first cut idea or guess on the natural frequency of the system. Okay. Now, that is how you do it for the lateral vibration problems. So, the summary of this lecture, we had discussed the effect of decoupling on the force transmissibility earlier, and in today's session we demonstrated that by a numerical example. We also got introduced to influence coefficient approach, and we applied this in studying the bending vibrations of a shaft. These are couple of review questions for you. And these are the corresponding answers.